is I'm going to talk a little bit about astronomy because of the Roche Loeb celebration I had the last time, but also because it has something to do with the one problem you're solving in the tutorial, right? So you have one problem in the tutorial that's just a dynamical system that's cubic in theta and is actually a potential system that I've asked you to analyze and look at. But it is a very famous dynamical system in that it helps us describe the orbits in both Newtonian physics and in general relativity, in fact. And we've had quite a lot of, we had the Roche Loeb, and the story of orbits and planetary motion is intertwined with dynamical systems from the start. I mean, Newton derived calculus or worked out calculus to be able to describe the motion around the sun. He solved it. The planetary motion laws, the fact that if you only have two bodies that move around each other in Newton's theory, you always end up with an ellipse. And in effect, that's what you're describing over there in the problem set is if you put epsilon in that problem set, which is the relativity parameter, to 0, you're actually going to find ellipses. Okay. The equation in your problem set describes the radius or 1 over the radius versus the angle, and the solutions you get out will just be ellipses. And then Einstein came along and he did the general theory of relativity, and it's quite complicated to derive the equation for two bodies where that thing comes from. But the fact is, once you've got it, it once again looks very similar to Newton's theory plus a correction, which is what you expect. And then it's just that cubic term that comes in and that you'll look at when you actually do the proper phase diagram analysis. The things that are possible when you have that epsilon term, the orbits are no longer ellipses. They change. It was one of the indications that Newton's theory was not complete. That was already anticipated way before Einstein was discovered. They noticed that Mercury's orbit precessed. In other words, by precession, I mean you have an ellipse, and Newton's theory, if you just have two bodies, predicts that that ellipse is just going to stay in the same orientation and it's going to stay like that. And they observed that Mercury's orbit did that very, very small in like a tiny 42 arc seconds a century. So it's a tiny movement that it made. But they'd already observed it before Einstein came up with his theory. And they said, well, there must be something else that's moving this orbit. It's not just the sun's motion. And then they came up with various possibilities that explained it, and none of them included relativity. There were easy ways to explain it. They said, well, okay, if the sun is not completely round, it's also going to make a difference. If there's a planet that's close that we haven't detected, again, it will also make something like that happen. So there were various other explanations for what they saw. Nonetheless, when Einstein came along and he worked out the theory and derived that expression for what the orbits are like, it matched perfectly with Mercury's theory. Okay, if you use general relativity to describe the sun and its gravitational potential and Mercury's motion, then it matches perfectly. It predicts what we see. So we've been seeing precession, or these orbits that sort of move around like that, in other places as well. Let me just get a piece of chalk. So what I've drawn on the board is just two ellipses, and by precession I mean that the major axis of the ellipse changes with time. Okay, and so we've seen it in other places as well. The one place we see it is in neutron stars, and we've measured it. There's a famous example where we actually saw that and we can detect it. The other one that's the most beautiful example that I've yet come across is about stars that go around our galactic center. Okay, and in fact, this was what they used to measure the mass of the galactic center. And so it was the subject of the 2020 Nobel Prize. And because I work with it so closely, I thought I'd share it with you, and because it's relevant to the problem set, I also thought I'd go through it. So the 2020 Nobel Prize was basically given to Roger Penrose, that basically discovered black hole formation and did a lot of theorems that I work on about what relativity predicts for black holes, what it means for the orbits, what it means for causality, whether you can see into a black hole or not. So he did a lot of theorems that way. And the second two people were experimental. They were Reinhard Genzel, which is in Europe. He's part of the Max Planck Institute. And the other one was Andrea Ghez, which is an American that's at UCLA. And both of these work with very, very powerful infrared telescopes. And what they did is they claimed for the discovery of the supermassive object at the center of the galaxy, but they did a lot more than that. They actually observed our galactic center. So if you want to know where our galactic center is, it's very visible at night here. If you look up and you see the Milky Way, then there's this region where this band of stars across, where it gets like dark in the bright part, and that's where our galactic center is. There's a lot of dust that way, and that's what made the observations of these things so difficult. And they looked at that, and they looked at that with a pretty amazing telescope. It's a binary telescope. It's two telescopes. So they can basically have two lines of sight through the sky, so they can cancel atmospheric effects, because they had to make a very, very precise measurement. So they're the first ones that actually managed to look at our galactic center, look really, really close to it, and they could see a bunch of very heavy stars moving around it. And all those stars were precessing like this, and they've been watching those stars for 15 years. And it turns out that that epsilon parameter that appears in your problem, but also appears in how the precession moves, is determined by the mass of the black hole. And so they actually used those observations to get several independent measurements for the black hole, or that's at the center of the galaxy. And they did more than that. They made the case, because remember, we're looking at it observationally. We can't just assume it's a black hole like Penrose predicted. We actually have to gather the observational evidence for what it is. So they basically used the stars and the precession of the stars to measure the mass that they can do. And they said that there's nothing else being radiated from it. So in fact, they made an argument that it's black, right? There's no other emission from it in that spectrum that they looked at. And it's a very, very powerful constraint that you have this extremely massive object sitting there that's behaving like a black hole. It's not radiating, and yet it contains all that mass. And we know of no other means besides it being a black hole at the moment. So they sort of did the detective story to try and describe it. So what they did, so this is basically, it tells you, if you want to know where we're looking at the sky at night. So oh dear. Okay, so where they looked was basically, I don't know if you want to hit the lights, or if you can see if you're fine. You happy? Okay. So where this is the Sagittarius A. There we go. Okay, so Sagittarius A, if we look up at night, and it's very nice for the southern hemisphere, you have the Milky Way, which is this band of bright stars, and then you have this teapot, which is actually quite easy to see. It's Sagittarius, the constellation, and then you have the Scorpion, which you can also identify because it's a huge one, and then you have this dark region, and this dark region isn't really dark. It's dark because there's dust that obscures it. In fact, when you look in this direction, you're looking at the center of our Milky Way, you're looking at the rotational center where our galaxy revolves around. So if you think of the Milky Way, you usually have this flat pancake, ours, and we're sitting out in the spiral arms, and if we look in that region, we're actually looking right into the center. So this is where we expect the black hole to be. One of the motivations for that as well is that everything else rotates around it. It's very, very massive. Okay, and so what they did is they did looked at a serious number of stars, the stars that get the closest. And now close around the black hole is relative, right? You can't get really, really close. It is still a very, very long way. So this is basically, this distance is 120 times the distance from the Earth to the Sun. Okay, this is how close the stars get to the black hole. So it's a much further away from the Earth is to the Sun, like 120 times, but it is much, much, much more massive. So the central thing that came from their measurements is that it's roughly 4 million solar masses that is stuck, that these stars are rotating around. They come about 120 times the Earth-Sun distance of the thing, and there's several stars. The one that approaches the closest is S2. They've named them all S with a number. S initially came from special star. Anyway, they approached this. They saw this the closest distance. They've approached. They saw this on the 19th of May, 2018. So this was the closest approach. It was very exciting because people was expecting all sorts of strange things to happen, and nothing did. It just went close and went by. But this star orbits the black hole every 16 years. So they have actually been watching this, and I'll show you the data now. For 16, they've been watching it for well over 20 years. Systematically, every year, they measure it with these very fine telescopes. They measure the whole star field, and they track them. And the speed that it's going at is roughly 25 million kilometers per hour, but that doesn't really make a big difference to the star because it's traveling through effectively vacuum. It doesn't really feel it that much. Okay, so that's the closest one. But it's not the only star that they've been observing. What they've been looking at is all these stars, okay? And they've literally been studying them. So here's that S2 that comes the closest. So this is a 15 or a 16-year period. Some of these, the further away they go, the longer the period is. It's basically a rough estimate of Kepler's law. And so these have periods of 32 years, so not all of them have completed orbits. So you'll see what they've actually seen. Okay, and literally they can use all these things and they measure how they are processing and they get the same answer. So let me just show you some of their... so this is actually what they see once they've cleaned up the atmosphere. So this is basically a couple of years. You can see up here the time period that they've been looking at it as it evolves. And this is, they've basically zoomed in, and I think this is there's S2 that they've been looking at. Okay, so this is what they basically do. They have a lot of technology that they've developed to look at their cameras, to take out the atmosphere, and then to clean up the images, and they record it regularly, and then and you can see that it's not perfectly, you see those error estimates on it. The position is not perfectly known, but they've had so many data points that they can actually track the orbit quite accurately. They've also done other things besides these stars. They saw comets go in, and they are really, this is like their thing. And they've done a huge contribution to the community, or what we know about the galactic center. Okay, so they are definitely the state-of-the-art group for making these measurements and actually seeing these orbits. And I'm pleased they were recognized, to tell you the truth. So I now want to show you a video that's actually going to put everything in context of sort of where these stars are really, really close to the black hole. And in fact, they're so close that the black hole completely dominates the way they move. They don't feel each other, they feel just the black hole. So I want to show you where it is to put it in context. Oops. So that's the Milky Way, and now we're going towards the galactic center. We basically started from our position in Earth. And this image, I think, is a double deep field image that we started from. Or not a deep field, a Hubble image. Okay, so that's what you would see through a telescope. So that blurry image gave you an idea of how difficult the thing is that they're actually looking at. Okay, so it's just zooming out again. So it's really the core of our galaxy that they've managed to look at and image. And then these are all the stars. The actual tracks give you how long they've been watching them. And mathematically, it's quite easy to see just the projection, but it's very hard to get the rest of the orbit to do, but they have done it. Okay. Okay, this is just another one of what the orbit does. It's the full reconstruction that they've made. And the nice thing about the way they measured it through all the different things to a given accuracy, get the same answer. So they're very, very sure that they have seen it. And what its mass is, and what its influence is on the surrounding stars. Okay, and you can see only the S1 has completed its orbit, but they all do that, and that angle that changes tells you how massive the black hole is.